Okay, so let us start today's session. Okay, so is the screen visible to everybody and am I audible?
Yes.
Okay, so mm, also if there is anybody waiting in the lobby, please do let me know so that I can let the person in as the meeting screen won't be visible to me. Okay, so let us start today's session. Uh, Good evening, everyone. My name is Abhik Deb, and I welcome all of you to the 10th live session of the course Concepts of Thermodynamics, which is being taken by Professors Dr. Suman Chakravarti and Dr. Aditya Bandyopadhyay at IIT Kharagpur. As in for myself, I am a PMRF PhD scholar in the Department of Mechanical Engineering at Indian Institute of Science, Bangalore, and I shall deal mostly with the live sessions of this course, wherein we will be discussing some of the problems uh, related to the concepts discussed in the previous class, so that it helps in better it will help the students for a better understanding of the concepts and also the applications of them, and also how to solve the problems. So I request all of you to be present every Friday from 6 to 7 p.m. and make this outreach a success. So without further delay, let us dive into our problems. And today we will be discussing the problems related to available energy and the related concepts that come along with it. So if you have any doubt, please do let me know so that we can clear it right then. Okay, so let us start. So okay, the first problem is a 2 kg piece of iron is heated from room temperature at 25 degrees Celsius to 400 degrees Celsius by a heat source at 600 degrees Celsius. The irreversibility in the process is what? So, what is irreversibility? Irreversibility is basically the decrease. The decrease in the available energy becomes is a measure of the irreversibility of the process. Okay, every particular body has a available energy with respect to its surroundings. So, whenever there is a process, there is a decrease in this available energy. This is due to the irreversibilities that are associated with the process. So, we have to find out what is the irreversibility associated with this process. Okay, so let us start. So the 2 kg iron piece is being heated from room temperature at 25 degrees Celsius to 400 degrees Celsius by a heat source. So the heat source will essentially lose the heat to this piece of iron for it to be heated. Okay, so what is the heat lost by the heat source? You can say, right, let us denote it with Q. This will be the heat gained by the piece of iron. Okay, so we are not considering that there will be any other losses to the surrounding and all. So we are considering that whatever heat is being lost by the heat, whatever heat is being supplied by the heat source is being taken away by the iron. Okay, so heat gained by iron, this will be the heat gained by iron. Okay, so this is mc delta t. Okay, so what is the mass of iron? The specific heat of iron is 0.42, it is given. And what is the change in temperature? Change in temperature is 400 minus 20. Okay, sorry, 25 it is. Okay, so this value comes out to be 315 kilojoule. So 315 kilojoule is being lost by the heat source. Okay, now the entropy change of iron due sorry. So when the iron is being heated from the room temperature to a higher temperature of 400 degrees Celsius, there will be a change in entropy as well of the iron. So what is the change in entropy of the iron during this process? This is the mass of iron into change in entropy during the process. Okay, so this can be written as mass of iron, and S2 minus S1 we can write it as Cp ln T2 by T1 minus R ln P2 by P1. But here P2 is equal to P1. Therefore, this term will be ln1, that is 0. Okay, so this will essentially be 2 into C. C for iron, for it is a solid material, so Cp and Cv will be same. So this is 0.42 ln T2 is 400, but we have to convert it to Kelvin, so it is 673, and I divided it by 25 degrees Celsius, that is 293 Kelvin. So this comes out to be equal to 0.6843 kilojoule per Kelvin. Okay, I hope this is till now this is clear. And entropy change of the heat source. That is, we are considering the heat source itself is the surroundings. So this is, since it is losing heat, so it is minus Q by T. Okay, so any losing of heat is accompanied by a decrease in the entropy. So this is what we have found out, 315 kilojoule. And what is the temperature of the heat source? 600 degrees Celsius. 600 degrees Celsius, that is 873 Kelvin. So this is minus 0.3608. 0.3608 kilojoule per Kelvin. Okay. So what is the net change of entropy of the universe? Universe is system and surrounding. So system is the iron and the heat source is the surrounding. Therefore, change in entropy of the universe surroundings. So this is what? This is 0.6843, 0.6843 minus 0.3608. Okay, so this comes out equal to 0.3234 kilojoule per Kelvin. Okay, therefore entropy generated is also this net change of entropy of the universe, that is 0.3234 kilojoule per Kelvin. Okay, therefore the irreversibility of the process I can say this is T naught into entropy generated. Okay, so we know this is from the Gauss-Stodler theorem. So this is 298 multiplied by what is the entropy generated. This is 0.3234 kilojoule. Okay, so this is 26 per, sorry, this is 96 0.3956 kilojoule, or you can say this is 96.4 kilojoule. Okay, so this is option number A. Okay, so this is the answer. So is it clear to everybody? If you have any doubt, please do ask. So if there is no doubt, then we will move on to the next problem. If you have any doubt, please you can ask. Okay, then sorry. Let us move on to the next problem. Okay, so a steam turbine receives steam at 6 megapascal 800 degrees Celsius. It has a heat loss of 49.7 kilojoule per kg. Okay, and an isentropic efficiency of 90%. The exit pressure is 15 kilopascal and the surrounding is 20 degrees Celsius. What is the actual work between the inlet and the exit? Okay, so what is happening here? The turbine is receiving the steam at 6 megapascal and 800 degrees Celsius, and along with a heat loss of 49.7 kilojoule per kg, it releases the whatever it is. It may be a steam or a mixture of steam plus vapor, sorry, steam plus liquid water, at an exit pressure of 15 kilopascal, wherein the surrounding is at 20 degrees Celsius. The turbine has an isentropic efficiency of 90%. Okay, so we have to find out what is the actual work between the inlet and the exit. Okay, so what is isentropic efficiency? Isentropic efficiency is essentially the ratio of the actual work to the isentropic work. Okay, so we can first find out the isentropic work, and then we can use this isentropic efficiency to find out the actual work. So at the inlet, corresponding to 6 megapascal 800 degrees Celsius, okay, S1 equals to 7.6469, and H1 equals to 4123.97 kilojoule per kg. Okay, at exit, now we are considering that the expansion process is isentropic. Okay, so at the exit, considering isentropic expansion, S2 S is equal to S1, and that is 7.6469 kilojoule per kg Kelvin. This 2s is here denoting that we are considering that the expansion is isentropic. That is, the point 2s is reached when there is an isentropic expansion process. Okay, now corresponding to SF is equal to 0.7545 74543 kilojoule per kg Kelvin, and Sg, this is equal to 8.0091 kilojoule per kg Kelvin. So you can see that S2S lies between SF and Sg. So it is a mixture of liquid water and vapor. So what is the quality here? S2S minus SF by Sg minus SF. So this is 7.6469 minus 0.7543, and this is 8.0091 minus 0.7543. So this value comes out to be 0.951. Okay. So what is the enthalpy in this? Therefore, H2S is equal to HF plus X2S into Hg minus HF. Okay. So this value comes out 225.85 plus 0.951, and this is 2373.51. Okay, so this comes out 2483.06 kilojoule per kg. Okay, so what is the isentropic work? Therefore, isentropic work this is equal to H1 minus H2S. Okay, so this is 4123.97 minus 2483.06. Okay, so this is 1640.91 kilojoule per kg. Therefore, isentropic efficiency. What is isentropic efficiency? Isentropic efficiency is actual work by isentropic work. Okay, so actual work will be isentropic efficiency multiplied by isentropic work. So this is 0.9, since 90% is the isentropic efficiency, and 1640.91. So this is 1476.82 kilojoule per kg. Okay, so the actual work between inlet and exit is 1476.82 kilojoule per kg. Okay, so this is the answer. So is it clear to everybody? If you have any doubt, please do ask.
Yes, sir.
Yeah,
Yeah, no doubt, sir. It is clear.
okay, thank you. Then we will move on to the next problem. Okay. Okay, so the next problem is that we have to find out what is the actual change in entropy of the steam during this process. Okay, so see, this is an isentropic work. Okay, this is not a real process. In real process there is also a heat loss. So if we consider the heat loss, and as we have already found out the actual work, so what is the actual considering that the process now, there is isentropic process won't be happening, only the actual process will be happening. And for the actual process, what is the change in the entropy of the steam finally, that we have to determine. Okay, so let us start with it. Okay, sorry. So yeah, let us start with it. So W actual that we have found out in the previous problem, we have found this out using isentropic efficiency now, but we also know that if we consider a energy balance of the turbine and in the actual processes, then this will be H1 minus H2, that is the entropy change in the turbine minus the heat losses that are occurring in the turbine. So this is just the energy balance, where H2, the point 2 denotes the point 2 denotes the actual exit point, okay, not the isentropic exit point, the actual exit point of turbine. Okay, so what we can do, so we already know what is the actual work, so we can find out this one out. H2 is H1 minus W actual minus Q loss. Sorry. Okay, so what is H1? H1 is 4123.97. We have already found all this out. Minus the actual work we have determined previously, 1476.82. And what is the heat loss here? See, essentially in the previous part we have not considered a heat loss, because what does isentropic means? Isentropic essentially has to be a reversible and adiabatic process, so there is no heat loss. But in the actual process there will be heat loss, and that is given as 49.7 kilojoule per kg. So this is 49.7 kilojoule per kg. So this value comes out to be 2597.45 kilojoule per kg. Okay, so but this value, it lies, you see, this value it will lie between the Hg and Hf values. So this is essentially a mixed state. Therefore x2 is equal to H2 minus Hf by Hg minus Hf. Okay, so this is 2597.45 minus 225.85, and this is 2373.51. 2373.51. So this value comes out to be 0.9991, which is very close to 1 though. Therefore the entropy will be 1 minus x2 into Sf plus x2 into Sg. So this value comes out to be 8.0032 kilojoule per kg Kelvin. Okay, so now what is the required actual change in entropy of the system? Therefore required actual change in entropy of steam, this is equal to S2 minus S1, that is 8.0032 minus the initial entropy was 7.6469. So this value is 0.3563 kilojoule per kg Kelvin. Okay, so this is the answer. I hope this is clear to everybody.
Yes, sir. Thank you very much. You are giving a step by step and a solution.
Okay, so it is, you are understanding
Yeah,
it, right?
yeah, yes.
Okay.
Sir,
Mm,
one
mm,
thing in this any question I understood no doubt,
mm,
but if you any represent this isentropic process and the actual process
mm,
on the diagram,
mm.
then it will be more simple.
Yeah, we can do that. So,
I already I know that one. I already understood.
hmm. So
Chakravarti
see,
sir already
you can also do it like
already.
this. I mean,
Yes, sir.
supposedly, if we are drawing this diagram, so if this is a process, okay, it starts from one, and this,
If it is
so
isentropic, then it is a vertical exactly.
yeah, this will be
And
vertical. So this is
actual
2s.
process is an deviate
Yeah, this will be deviated
inclining.
like this. Okay. So isentropic efficiency, if you also calculate directly from the table, you can also use it the isentropic efficiency as H1 minus H2 divided by H1 minus H2S. So that will also give a similar result. Okay.
Me Chakravarti sir already and explain all this anything in a very good manner.
Okay.
There is no question at all.
Okay. Okay.
This I mean,
Yeah.
yeah,
Yeah. Yeah. Okay.
yeah.
Then let us move on to the next problem then.
Okay,
Yeah.
okay.
Yeah. Sure. Okay. So this is a 1 kg block of copper at 350 degrees Celsius is quenched in a 10 kg oil bath initially at ambient temperature of 20 degrees Celsius. Okay, so these are two parts. Okay, a block of copper is now dipped into a oil bath, which is initially at an ambient temperature. Assuming that there is no heat transfer from and to the ambient, other than the oil bath, there is nothing with which the block of copper is exchanging heat. The final uniform temperature of the system is what? So this is basically a very pretty straightforward energy balance problem, but actually we will be needing it in the next part of the problem, so we will have to do this. So let us start. So from the energy equation, okay, but we know dE by dt, this is equal to Q1 to 2 minus W1 to 2. Okay, so what we can write it as M2 U2 minus M1 U1, and this is 0 minus 0, since both heat and work here are 0. There is no heat transfer, there is no work done. Okay, so this is the final mass, this is the final internal energy, and this is the initial internal energy. So what is the final internal energy? Final internal energy will be mass of copper, C for copper, T for copper. Okay, but not T for copper. This we are assuming that the system comes to a final uniform temperature, which we are assuming as, let us say, T2. Okay, so we can write is, let the final uniform temperature of the system be T2. Okay, so this is T2 plus mass of oil, C for oil, and T for the final temperature. Okay, and this is initially, what is the initial temperature? T copper initial, say I, plus mass of oil, C for oil, T for oil initial. So we can write it, we can combine and write it, or we can just keep it separately also. So what is the mass of copper? 1 kg. C for copper 0.42. T2 we have to determine. Mass of oil is 10 kg. C for oil is 1.8 and T2 we have to determine again. Okay. So and this one is 1 multiplied by 0.42. What is the initial temperature? Initial temperature is 350 degrees Celsius. 350 degrees Celsius is 623 Kelvin. Plus this is 10 kg 1.8. And what is the initial temperature? The oil bath is initially at the ambient temperature itself of 20 degrees Celsius. It is 293 Kelvin. Okay. So what is the final temperature? T2 0.42 into 623 plus 10 into 1.8 into 293 divided by 0.42 plus 10 into 1.8. Okay, so this temperature comes out to be 300.52 Kelvin. Okay, so therefore the required final uniform temperature of system is 300.52 Kelvin. Okay, so this is pretty straightforward. So the data will actually be required in the next part of the problem. So let us directly move into it. In the previous problem, we have to find what is the change in the availability of the system. That is copper plus oil we are considering as a system. Then what is the change in the availability of the system? So for both copper the for both copper and oil, the availability function can be written as phi equals to u plus p naught v minus t naught s. Okay, so this is the basically the availability function of a closed system in which there is no flow. Okay, now for the change in state, this delta phi, it can be written as phi 2 minus phi 1 or u2 minus u1 plus p naught v2 minus v1 minus t naught s2 minus s1. In this system there is no change in the volume, so this term will essentially be 0 for both copper and oil. Okay, so for no change in volume, delta phi is equal to u2 minus u1 minus t naught s2 minus s1. Okay, therefore delta phi of the copper u2 minus u1 for copper minus t naught s2 minus s1 for copper. So this can be written as mass of copper, since these we have this will be converted to specific differences now. So mass of copper multiplied by u2 minus u1 is Cp, C for copper, and T2 minus T1 minus T naught into S2 minus S1 can be written as C ln of T2 by T1 minus R ln of P2 by P1. Now there is no change in the pressure as well, so this will be 0. So this value comes out to be, and T2 is the temperature, common temperature that we have initially found out at 300.52 Kelvin. Okay, so let us put in the values. So this is 1, right, 1 kg of copper. This is 0.42, 300.52, and initial temperature of copper is 623 Kelvin. The ambient is 20 degrees Celsius, so 293 Kelvin. This is 0.42 ln of 300.52, and this is 623. Okay, so these values comes out to be minus 135.14 minus of 89.71, that is finally this value comes out to be minus 45.42 kilojoule. Okay, and the change in available energy of oil, this is equal to U2 minus U1 of oil minus T naught into S2 minus S1 of oil. Okay, so this is 10 multiplied by 1.8 into 300.52 minus initially temperature is 293 minus 293 multiplied by 1.8 multiplied by ln of 300.52 by 293. Okay, so this value comes out to be, this is 135.36 minus 133.65. So this value comes out to be 1.708 kilojoule. Okay, therefore change in available energy of the system is equal to change in available energy of the copper plus change in available energy of oil. So this is minus 45.42 plus 1.708. So this value comes out to be minus 43.71 kilojoule. Okay, so this is the change in availability. What are we supposed to find? The change in availability of the system that is copper plus oil, that is minus 43.71 kilojoule. Okay, so there is a net decrease in the available energy. Okay, I hope it is clear to everybody, and we will then move on to the next problem. Okay,
Sir, hello, sir.
yeah, hi.
Sir, can you show the second page of this
Your
problem?
voice is not audible.
Uh, Hello.
Yeah, hi. Yeah,
Sir, please show me the second page of this solution of this problem.
okay,
I
which is
have
the second page?
for a little of time I was out of here. I will
Okay, so
note.
this page, right?
Yes, sir. This
Okay,
also the first page also.
okay, this is the first page.
Okay, sir. Just wait. Okay, sir. Second page.
Okay,
Okay, sir. Thank you.
okay. I think so. You, I mean, these are all available, right? These resources are being made available to you, right?
Sir, I am actually noting this one. but for 5 minutes I was in out of.
Okay,
That's
okay,
why I have not noted
okay,
today.
okay,
Okay,
fine.
thank you.
Okay, let us then move on to the next problem. Okay, so now the steam enters a turbine at 25 megapascal, 550 degrees Celsius and exits at 5 megapascal, 325 degrees Celsius at a flow rate of 70 kg per second. There is no heat transfer to and from the turbine. The total power output of the, what is the total power output of the turbine, we have to determine. Okay, so this is also pretty straightforward. At the inlet corresponding to 25 megapascal and 550 degrees Celsius, the enthalpy is 3835.6 kilojoule per kg. Okay, and S1 equals to 6.1765 kilojoule per kg Kelvin. Okay, and at the exit corresponding to 5 megapascal and 325 degrees Celsius, H2 is equal to 2, sorry, H2 equals to 2996.5 kilojoule per kg and S2 equals to 6.3289 kilojoule per kg Kelvin. Okay, therefore, from the energy equation, for steady flow process, H1 equals to H2 plus work done by turbine. Okay, so work done by the turbine is H1 minus H2. So this value comes out to be 428.31, sorry, 428.31 kilojoule per kg. Therefore, what is the total power output? Will be this mass flow rate, that is 70 kg per second, multiplied by the specific work output. So this is 70 multiplied by 428.31. So that comes out to be 23737. So this is 23737 kilowatt. Okay, so this is very straightforward. So the problem, the data will be used now. So in the previous problem we have to find what is the isentropic efficiency of the turbine. Okay, so isentropic efficiency is basically what? Isentropic efficiency is the ratio of the actual work to the isentropic work. Okay, so for isentropic expansion process, S2S is equal to S1 and that will be 6.1765 6.1765 kilojoule per kg Kelvin. Okay, So corresponding to 5 megapascal, where 5 megapascal is the original exit state, corresponding to 5 megapascal, SF equals to, sorry, we don't need to find that, corresponding to 5 megapascal, when the entropy is 5.9714 kilojoule per kg Kelvin, the enthalpy is 2796.74 2796.74 kilojoule per kg. And when the entropy is 6.2087, the enthalpy is 2924.84 2924.84 kilojoule per kg. So this value of entropy lies between these 2 points. So we have to find out the corresponding enthalpy value at 5 megapascal by interpolation. Okay. Therefore, H corresponding to, let me write it. Therefore, corresponding to 5 megapascal and S2S equals to 6.1765, the enthalpy value is 2796.74 plus 2924.84 minus 2796.74 2796.74 divided by 6.2087 minus 5.9714, and what is the difference here? 6.1765 minus 5.9714. So this value comes out to be 2907.29 kilojoule per kg. Okay. Therefore, the isentropic work of turbine is H1 minus H2S. So what is H1? H1 is 3835.6, 3835.60 minus 2907.29. So this value is 428.31 kilojoule per kg. Therefore, the isentropic efficiency is equal to the actual work. By this we can write it as isentropic work. So W isentropic. So what is the actual work? Actual work is 428.31. Sorry, there is some issue. This is I have made a mistake here. This won't be, this will be 339.10 339.10, and so this is same. This is 23737. So this will be 339.10, and this is 428.31. So this is actually 0.7917. Okay, or we can say that the isentropic efficiency is 79.17%. Okay, okay. So hope it is clear. Then there is another part to this problem. We have to, in the previous problem, we have to find what is the second law efficiency of the turbine. Okay, so what is the second law efficiency? Second law efficiency is, the second law efficiency is equal to the actual work by the reversible work. Okay, so what is the reversible work? Reversible work is the maximum work that can be possible from a process under reversible conditions. Okay, when there is no irreversibility, this has nothing to do with the isentropic process or anything. This has to be a completely reversible process. Then if there is a completely reversible process, then what is the maximum work that can be obtained from it? That is the reversible work. Okay, so where W reversible is equal to the reversible work output of the system considering the same inlet and exit state. This is very essential. Okay, between the same inlet and exit state only will the reversible work be considered. Okay, so we know W reversible is actually W reversible minus W actual is the irreversibility. Okay, so W reversible is W actual plus irreversibility. Okay, and W actual, and what is the irreversibility? Irreversibility is again T naught into entropy generated from the Gauss-Tordola theorem. So we can write it as W actual plus T naught, and entropy generated is what? Entropy generated is the net change in the entropy of the universe, that is the system plus surrounding. So this is a turbine and there is no heat transfer to and from the turbine with the, that is other than this process, that is the expansion process, there is no heat interaction with its surroundings. So the surrounding work becomes zero. So what is the change in the entropy of the universe? That is the entropy of the system itself, and that is S2 minus S1 plus, if you do this one, then there is no heat interaction, so this is zero. Okay, so let me write in the values. What is actual? 339.10 plus what is the ambient temperature? Ambient temperature, let us consider as 25 degrees Celsius, which is the usual temperature of the surroundings, which we consider if there it is not given. So, and S2 minus S1, that is 6 point, what is the final entropy? 6.3289. See, we are not considering the isentropic process here, because isentropic process is we have to consider the reversible process and not the isentropic process. So the reversible process has nothing to do with the isentropic process that we considered before. So the original exit state is 6.3289 entropy. So 6.3289 minus the initial is 6.1765 that is the inlet, 765. Okay, so this value comes out to be 339.10 plus this is 45.41. So this value is 384.51 kilojoule per kg. Okay, therefore the second law efficiency is equal to W actual by W reversible. So this is 339.10 by 384.51. So this value is 0.8818 or 88.18%. Okay, so this is the second law efficiency. Okay. So is it clear to everybody?
Yes, sir.
Okay, then let us move on to the next problem. So a flow of 2 kg per second water at 1000 kPa 80 degrees Celsius. So this is water at 1000 kPa and 80 degrees Celsius. It enters a counter flowing heat exchanger. Okay, in which it is a counter flowing heat exchanger is essentially a constant pressure boiler. I mean, what happens in the boiler? In the boiler there is a uh, mm, I mean, two fluids, they exchange heat so that one of the fluids get converted to a vapor, which can be expanded in the turbine. Okay, so in this process, it is basically both boilers and a condenser, both are heat exchangers itself. So in a counterflowing heat exchanger, the boiler is designed as a counterflowing heat exchanger of constant pressure configuration, in which the water enters at 1000 kPa and 80 degrees Celsius and leaves at 1000 kPa 400 degrees Celsius. And the hot gas that heats the water, it is air and it is coming in at 1200 Kelvin and it leaves at 900 Kelvin. So in this process, due to this heat exchange, what is the total rate of irreversibility in this process? Okay, so for water, let us start. uh, for water, okay, at 1000 kPa 80 degrees Celsius, it will be in a compressed liquid state. Okay, so the water is essentially entering as a compressed liquid. H1 is 335.64 kilojoule per kg, and at 1000 kPa 400 degrees Celsius for compressed liquid, it will be a superheated steam. Okay, so in this case the enthalpy will be 3262.82 kilojoule per kg. Okay, again for air at 1 atmospheric pressure and 1200 Kelvin. Okay, this, what is the enthalpy? Enthalpy is 1278.68, and at 1 atmospheric pressure 900 Kelvin, the enthalpy is 933.99 kilojoule per kg. Okay, we know now we know from the basic energy balance, the mass flow rate of water into H2 minus H2 minus H1, that will be taken by the air and its enthalpy will decrease. This is an increase in enthalpy, this is a decrease in enthalpy. Okay, so what is the, now we know the mass flow rate of water, so what is the mass flow rate of air? That will be H2 minus H1 by H3 minus H4. Okay, so if we put in the values, the mass flow rate of air, this is equal to 3262.82 minus 335.64. Okay, and this is 1278.68 minus, sorry, this will be 933.99. So this is 16.98 kg per second. Okay, so now the change in availability of water, both are, the water and air both in this case are flowing systems. Okay, therefore change in available energy of water in the process one to two is, this will be delta psi W. Psi is for the flow system, so this will be mass of water H2 minus H1, okay, minus T naught into S2 minus S1 for water. Okay, so what is the mass of water? 2. Okay, this is 3262.82, 3262.82 minus 335.64, 8.64 minus T naught is 298, 7.4634, 1.0747. Okay, so this value, we write it here, this value comes out to be 2046.69 kilowatt, 2046.69 kilowatt. Okay, so there is essentially an increase in the available energy of water here, and change in available energy of air in the process 3 to 4 is delta psi air, mass flow rate of air H4 minus H3 for air minus T naught S4 minus S3 for air. Okay, so this is 16.98, H4 minus H3 is 933.99 minus 1278.68 minus 298, 8.0158, 8.3497. Okay, so this value comes out to be minus 4163.28, minus 4163.28 kilowatt. Okay, therefore change in available energy energy of the system, that is system is both water and oil, water and air, is equal to minus 4163.28 plus 2046.69. Okay, so this value comes out to be minus 2116 kilowatt. Okay, so minus sign denotes that there is a decrease in available energy. Okay, so the rate of irreversibility is the decrease in available energy. Therefore, rate of irreversibility this is also rate of change in available energy. Okay, oh, rate of, and this is rate of irreversibility will be the same as the rate of decrease in the available energy, that is 2116.59 kilowatt. Okay, so I hope this is clear. Then in the next part of the problem, that is in the previous problem, we have to find out what is the second law efficiency of the boiler setup. Okay, so boiler is essentially a heat exchanger. So for heat exchanger, we do not consider the work done. We consider what is the maximum heat exchange possible and what is the actual heat exchange that has happened. So in the counter flow heat exchanger, the maximum heat energy obtained from air is mass of air into psi 3 minus psi 4. That is this value, basically this change in um, available energy during the process, that is psi a. That comes out minus 4163.28. We are only taking the sign, because only taking the magnitude, because this is the energy that is lost from air, so the negative sign would have indicated a loss in energy from air. So, but since we are obtaining the energy, we are considering what is the energy obtained, so we are just considering the magnitude, and actual heat energy absorbed by water is mass of water psi 2 minus psi 1, and this is essentially this, the increase in available energy of water, that is 2046.69 kilowatt. Therefore, the second law efficiency, this is the maximum energy that can be obtained. Okay, so air is the source of energy, and this is the maximum energy that can be obtained from air, and this is the actual energy that is absorbed by water. So the second law efficiency of the boiler setup, that is equal to this value 2046.69. We are dividing it by the maximum energy that is possible to be obtained from here in this process. So this value, this comes out to be 0.4915, or this is 49.15%. Okay, okay, so is it clear to everybody?
Yes, sir.
Okay,
Sir, actually, in the last week, I miss your any session.
okay, okay,
That transparency is any available, sir?
Yeah, actually, you can go to the YouTube and you can search for this concepts of thermodynamics recordings, and there will
Uh,
it will find you will find it.
Okay, okay, sir.
Yeah,
And that is the only class I miss.
yeah. I found out that you were not present.
Yeah.
Anyway, okay. So, okay, then let us meet in the next class. Please attend.
Okay, okay. Thank you very much, sir.
Okay, see you
Okay,
in the next week. Okay.
okay, sir.